Imagine a drone that transforms, that connects to other drones mid flight in open air and becomes a larger, more capable vehicle. Then it separates again. This is the concept behind this project. But before any flight, there is a question that needs to be answered. Can the structure hold? Conventional unmanned aerial vehicles are highly specialized, designed for one mission, one configuration, one predetermined role. Modular reconfigurable aerial vehicles break that paradigm. Independent modules that can dock and separate autonomously, allowing for payload capacity, configuration, and functionality to be adapted for each mission. The coaxial swashplateless architecture reduces mechanical complexity, but this creates significant structural challenges in force transfer between modules, in vibration control, and in the selection of materials that are both lightweight and resilient. But this work didn't start from scratch. The previous group established the MRAV concept, developed initial CAD, built prototypes, and identified critical structural limitations, excessive vibration, inadequate materials, and interfaces that needed to be rethought. That's exactly where my work began, with those limitations, with a clear objective to address them, to design and validate a lightweight, robust, and numerically verified structure, a structure built to fly. I developed and compared three distinct opening mechanisms: a rotary fitting, the snap fit, and the slide system, which was the one selected. Material selection. After a comparative analysis, I chose carbon fiber reinforced PETG over PLA. 31% higher young modulus, better fatigue resistance, and better stiffness to weight ratio, the choice was justified. The full structure design and finite element analysis in Siemens NX with two load cases. Hover at 100% throttle, in normal landing with 3G dynamic impact factor. In the modal analysis, the natural frequencies ranged between 40 and 71 Hz, 37% higher than PLA, which significantly reduces the risk of resonance with the rotor excitation frequencies. In hover, the von Mises stress remains well below the 51.4 megapascal allowable limit for PET-GCF. In landing, the critical load case, PET-GCF exhibits 24% less displacement than PLA. The maximum stress under a 3G impact are close to the allowable limit. The design is structurally marginal in this scenario. The structure is numerically validated, the material is chosen and justified, and the design limits are clearly mapped. The question I started with now has a well founded answer. It will